Can you all, there we go. Hi everyone, thanks for coming in. I know it's right after the lunch break, so I appreciate you coming in pretty early. My name is Kabir, and today I'm going to be presenting some of our work at Netflix. So this work is a bit off the beaten path when it comes to reinforcement learning for recommender systems. Rather than looking at the more typical use cases of applying reinforcement learning to recommendations directly, here we're going to be looking at applying reinforcement learning to optimize the data pipelining infrastructure that's used to build deep recommendation models. So here's the agenda for today. I'm going to start with a brief overview of recommendations at Netflix just to better set the context for this work. So recommendations at Netflix. The user experience with Netflix, it's almost entirely personalized. From the personalized billboards that show up at the top of the screen, to the row orderings, to the column orderings, even the art boxes and thumbnails that represent items in our catalog are personalized. Now, how do we achieve this level of personalization? It's a combination of two things. First, we have a large, rich corpus of data spanning user watch histories and interaction histories with our content. We combine this with a variety of models, all built around personalization and the user experience. And one common class of models that we use are DLRMs, or deep learning-based recommender models. The idea behind these model architectures is fairly straightforward. Given an input sample consisting of categorical features and continuous features, the categorical features are mapped into continuous vectors via embedding tables, then combined with the continuous features to produce user item interaction probabilities. Now, what kinds of challenges do we see when training these kinds of DLRMs at scale? Well, one of the main challenges we see comes down to dataset scale. Recommendation datasets tend to be massive. When you think about the amount of interactions that are generated for a popular service with millions or even billions of users, the datasets tend to be in the scale of terabytes, petabytes, or even exabytes. And despite all that, we still have to meet fairly restrictive training time SLAs. These models have to be updated on a daily cadence or a weekly cadence, so we need to be able to process and train over these huge data sets within a fairly limiting period of time. So that's one challenge that really motivates us to explore performance optimization for DLRMs. Another aspect here comes down to computational cost. DLRMs are typically trained on expensive, high-memory GPUs. When we look at submissions to the MLPerf training benchmark, the submissions there for recommender models often used thousands of A100 GPUs for a single model. So that gives you a sense of the scale of the compute used to train these models and why we're so interested in trying to reduce training times and thus optimize our costs. Another aspect here comes down to the commercial value of DLRMs. Even marginal improvements to DLRM quality can potentially yield significant incremental revenue for businesses. As a result, we're strongly motivated to try and explore multiple model configurations, train on as many datasets as possible, train different models, larger models. So to ensure maximum experimentational velocity, we again need to ensure that our DLRM training pipelines are as optimized as possible. All three of these factors together turn out to be strong motivators for us to invest heavily in training optimizations. But when we look at DLRM training optimization, the question is, which part of the pipeline is important? Now, it might be natural to think that the model execution on the GPU itself is the biggest bottleneck. That's what we need to tackle. But that's actually not the case. At the core of these DLRMs are the embedding tables. And the funny thing is that embedding tables are actually quite light in terms of compute. All they're really doing is an index lookup. Compare that to operations such as self-attention or convolution, which are much more computationally intensive. As a result of this, when we look at DLRMs in the literature and contrast them against LLMs or computer vision models, DLRMs are often orders of magnitude larger than these architectures in terms of parameter counts, largely due to the embedding tables, but orders of magnitude lesser in terms of computational demands. And this interesting contrast leaves us in a tricky situation. We need the latest and greatest hardware in order to handle these models and fit them in memory. But we're not making the best possible use of the GPU compute. Now, if we contrast this to the data pipelines that are used to train these models, this is the online data ingestion, the process of loading data from disk, batching it, shuffling it, augmenting it, and deriving new features right at training time. The operations that are used in this procedure are often quite compute and time intensive. When we look at previous studies of recommender pipelines, we find that this is a significant cost. In fact, Meta did a study of their DLRM training cluster, and they found that for one of their models, 56% of the time, the GPUs were idling and just waiting for the CPUs to finish processing the data and feed it to the GPUs. When you consider the scales and expenses which are operating, 56% GPU idling time is utterly intolerable. We have to try and address this bottleneck. So what is the result of this characteristic of DLRM training on our own clusters? Well, here we have a spread of traces taken from our cluster, where we analyze the degree to which these jobs are bottlenecked by data loading. So what you'll see here is that the vast majority of our jobs are bottlenecked to some extent or another by data loading. The spread is anywhere from 20% bottlenecks to 90+%. So what I mean by that is that 90+% of the time of training is spent purely on data loading, with the model just waiting on the GPUs for the data to be loaded. These numbers are obscene. We can't be waiting for the model. We can't be waiting for CPUs this entire time. Now, to some extent, this depends on how you construct your pipeline. We contrast three different categories of pipeline construction methods here: human-optimized pipelines, completely unoptimized pipelines, and pipelines that were constructed using automated tools such as TensorFlow's AutoTune. Regardless of the method of construction, all of them are still bottlenecked. So we definitely see room for improvement and a long gap to close in terms of performance. The other challenge we see on our cluster is that a lot of automated tooling for pipeline construction and optimization is not compatible with standard techniques such as machine resizing or autoscaling. When we change the number of CPUs available to a job over its lifecycle, we should expect the data loading throughput to increase because there are now more resources available for pipeline processing. But instead, with most of these tools out of the box, we see that they're not able to take advantage of these new resources. Instead, we have to rely on manual human intervention to checkpoint and relaunch the optimizers to make use of the new resources. So again, this is not ideal. The third problem we see is that a lot of optimized tooling out there to address this problem for data loading bottlenecks, it's not built around these complex, memory-intensive recommender pipeline operators. And so as a result, in trying to optimize the pipeline, they often end up over-allocating memory, leading to crashes and out-of-memory errors. In fact, with automated tooling, we saw an 18x higher failure rate compared to other jobs, which is completely unacceptable for our production use cases. So what do we want? We want a solution that can enable higher throughput in the data processing pipeline to alleviate these bottlenecks. We need our system to be aware of resource usage and memory usage to avoid out-of-memory errors and crashes. We also want our solution to be adaptable to deal with machine resizing and rescaling. And so we look to reinforcement learning as a solution. So we're finally at the session topic here. So that brings us into our solution, InTune. So first of all, the question might be, what is the problem of pipeline optimization here? What do we actually want our tool, InTune, to do? Well, if we think of the data processing pipeline as a series of stages, loading from the disk, batching data, shuffling it, any number of user-defined functions for feature transformation and data augmentation, and ultimately prefetching onto the GPU. Our problem here is essentially a resource distribution problem. We can parallelize individual stages of the pipeline with CPUs and providing memory for more resource usage. So we just need to figure out how to distribute the CPUs and memory available to our job over the pipeline. So that's what we're aiming to do with InTune. We're trying to do a reinforcement learning agent for resource distribution. So what does our agent actually need? First, we need to consider environmental factors. Hardware, the number of CPUs available, the amount of memory available, CPU processing speeds, pipeline latency. Next, the agent itself. We use a simple DQN approach with a very simple 3-layer MLP for the agent. We want it to be as simple as possible to avoid it contending for resources with the model execution itself. The action space is, again, fairly simple. It's about raising and lowering resource allocations for each stage of the pipeline. And our reward function is essentially just pipeline throughput normalized against resource utilization. The normalization is necessary to avoid it over-allocating resources and potentially leading to crashes. The system architecture is, again, fairly straightforward. We take in a data pipeline specification written in a standard deep learning framework. We wrap that under our agent, use that to produce new optimized pipelines, use that to feed data into the model, collect performance feedback to create the reward, and update the agent over time. The agent can, of course, be pre-trained offline on historical data pipelines and then updated online again for the ongoing training. This process turns into an iterative optimization problem where it's slowly shifting the resource distributions across stages to finally achieve that optimized pipeline that maximizes throughput. So now let's get into the evaluations of InTune. So in our results here, on the y-axis, we're going to show normalized throughput against an unoptimized baseline. On the x-axis is the job lifecycle. We're also going to show our performance under auto-scaling regimes, so we're going to change the amount of CPUs available to the job over time. And here are the results. InTune in yellow is at the top. And what we see here is that against manually augmented approaches where the human is intervening to help with auto-scaling procedures, InTune is still as much as 20% faster than these approaches. And against out-of-the-box systems, it's often more than 2x faster in terms of data pipeline throughput. And this is true both on the Criteo dataset and as well as our internal Netflix data pipelines. So what can we take away from this study? First of all, we can see that reinforcement learning turns out to be an effective tool for these resource distribution problems, especially in situations where the pipeline is user-defined and we're treating these as black box performance models. We don't have theoretical principles about how the pipeline performs up front. We also see a new avenue for reinforcement learning to be applied to improve recommendations, the system infrastructure side for DLRMs. In fact, we saw that with InTune, applying reinforcement learning to this problem space, we're able to produce a faster, more adaptive solution that's better suited to the needs of DLRM training. So some future directions we could look at here might be for InTune to help with caching decisions. Where in the pipeline should data be cached to be saved across multiple epochs, multi-machine scaling, distributing resources across multiple CPU nodes, or potentially even GPU resource allocation across multiple jobs for distributed training. Okay, so that's it for the talk. I'm happy to take any questions.
If someone prefers, you can write your question on Slido. Okay, so don't see any questions coming in, so I got one question. So you explained well. First of all, thank you for the clear presentation. You explained well why reinforcement learning is important for this task. I'm curious to know if you tried other methods that are not reinforcement learning, if you just take it as a regular regression problem, for instance.
Yeah, so there are a few reasons for that. One is the fact that we're essentially interacting with this pipeline as a black box. A lot of these functions are user-defined operators, which we don't have upfront performance models for, so we can't incorporate them into the optimization problem because we have no data on them upfront. We need to learn about them on the fly, and so reinforcement learning seemed like a good solution for that. We did benchmark against other solutions, such as an ILP-based solved approach. One of our baselines that we compared against, Plumber, uses a linear programming solution, and AutoTune uses a hill climbing solution, and we're able to outperform both of those. So we did benchmark against some other approaches to this problem.
Got you, thank you. Another question that I would like to ask, how quickly does it adapt to new hardware that you got? If there's a new, any type of hardware actually, with a storage or compute?
So when you say that, you mean in the auto-scaling setting, when new resources become available, how long does it take to re-optimize?
Right, and if there's a new type of server that you have never seen while you train the original model.
I see. So typically what we saw is that it's able to converge to a more stable or optimized position within just a few hundred iterations. So when you consider a training job which is going for millions or billions of iterations, this upfront 100 iteration optimization period is pretty negligible.
I see. Thank you. I would like to thank the speaker again.